Hello calculus fans. Today we start section 8.1 which talks about arc length. So to measure the arc length of a curve, we start by breaking the curve into small segments. We then approximate the curve segments using line segments and add the length of the line segments to form a Riemann sum. These line segments, of course, tend to become better and better approximations to the curve as the number of line segments increases. And as the number of segments increases toward infinity, the corresponding Riemann sum approaches a definite integral whose value will be the arc length of the curve. So you can imagine it like this. Let's say we've got this curve that goes like this. I'll copy it a few times here. So some kind of curve like this. Well, we could approximate it with a couple of line segments, like say here and here, and do a straight line segment. We could use that, and it wouldn't be that great. So then maybe we break it up into 3 line segments. We approximate it with these straight lines, and that's better. And of course, if you wanted to make it even better, you just break it up into more line segments, right? Same as pretty much what we always do in calculus. We break it up into many pieces and add together the little pieces. So that's the general idea. So suppose we have this curve here, and we want to measure the length of this curve. So let's say we want to measure the length of this curve between points A and B. So we're going to want to break up this interval here into n, we'll say n subintervals. So we have something like this. We break this up into a bunch of pieces, and then here are the points we're going to use. So we're going to look at straight line segments between each of these points, and we can figure out the length of a straight line, and we'll add up all these straight lines, add up the lengths of all these straight lines. So we'll have these lines that will connect each of these points. We use these straight line segments, the length of them, to approximate the length of the curve. So let's just take a look at one of them. Let's just say we have this one right here, and let's just say we take this, I'm going to move it over here just so we can get a better picture of it. Okay, so here we've got this blown up piece here. So of course the black line is the curve. This blue line is our straight line that we're going to use to approximate it. So what we're going to do is we'll call this this little piece of the curve, we're going to call that delta S, or S will be sort of like the arc length. And then this little thing, this little straight line segment, we're going to call D for distance. And what we'll do is make a little, let me fix that a second. We'll make a triangle here. And then what we'll do is we'll call this delta Y and this delta X. So you can imagine, like right here, make a little triangle here. And then this will be the change in X, and this will be the change in Y, right? Delta X, delta Y. And then this is delta S, the actual change in the arc, the little change in the curve itself. And then this little d is just the distance. Okay, and then you can see by looking at this, so this is actually going to be a right triangle. So we can use the Pythagorean theorem here, and we could say that delta x squared plus delta y squared equals d squared. Okay, so of course d is not the length of the curve, it's the length of the straight line segment. But as delta x and delta y get smaller and smaller and smaller, these two distances will get closer and closer. Okay, so we've got n subintervals here, so let's just put some of these last pieces together. They're n subintervals. And of course, we're going to use limits, so n will be approaching infinity. And we know that as there become more and more of these subintervals, they're going to get the change, this little delta x will get smaller and smaller and smaller. So this will get smaller, this will get smaller, and the arc length itself will get smaller. So we have these n subintervals, and just to make it official, let's just say this. So we know that as n approaches infinity, as the number of subintervals gets smaller and smaller and smaller, what will happen is this. Delta x will approach dx, delta y will approach dy, and delta s will approach ds. Remember these different notations, typically like delta x means a change in x, but dx means like once a limit has been taken, so maybe an infinitesimal change, although it's not really called infinitesimals, but it's like the change in x when a limit has been taken, right? So delta x becomes dx, and the others follow suit. As n approaches infinity, these things become smaller and smaller and smaller. Delta x becomes smaller and smaller and smaller, and so forth for the other variables. So what we're saying is that this tiny piece of arc, these little changes in x and y become smaller and smaller, it's going to act like a straight line segment. It will act like these will be very close to each other. And as the final limit in the limiting value, when we take the limit as n approaches infinity, then these will be each other, right? These will be the same as a limit, right? Remember, we're going to use limits here so that we can treat this delta s as a limiting value as it will act as if it is a straight line, like this little d here. So with that in mind, let's go ahead and take a look at this. So this, of course, is just from here, from the picture. So if I were to solve this for d, okay, so solve it for d, I'm going to take the square root of both sides. So we would get d is equal to the square root of delta x squared plus delta y squared. Now delta s is approximately equal to that, right? Delta s is approximately equal to d, so it's approximately equal to delta x squared plus delta y squared. Right, if you look at that picture we drew, little d and delta s are pretty close, and as the number of subintervals gets smaller and smaller and smaller, these get closer and closer and closer. So delta s is approximately equal to this. Okay, then here the limit comes. So we say as n approaches infinity. As that happens, then we'll get that ds equals dx squared plus dy squared. So as a limiting value, we can say that this is true. And then what we're going to do is we're going to use differential notation here. So as a reminder, if we have differential notation, probably remember this from Calc 1, and it comes up from time to time. So differential notation just means if we have dy dx, we're not thinking of this like the symbol dy dx, which means like y prime or the derivative of y with respect to x. We're thinking of it as a true fraction, dy divided by dx, where these dy and dx are separate entities called differentials. So we can treat them as their own entities, dy and dx. Okay, so with that in mind, what we're going to do is take this, and I'm going to factor something out. Okay, so let me write it down and then we'll take a look at it. Okay, so let's take a look. So I went from here to here. Now you can check this. If we distribute this dx squared through here, if we distribute it through here, we'll get 1 times dx squared, which gets us here. And when it comes through here, it would cancel the denominator and gets us here. Right, so using differential notation so we can do this. And then what we're going to do, basically I'm going to use the idea that if we have, let's say, a times b under the radical, we can break up radicals like this. As long as we're multiplying, right, or dividing, but it's not true if we add or subtract, but when we're multiplying, we can do this. So I'm going to treat this as the square root of this times the square root of dx squared, right? Because if I treat it separately, then we can have it come out of here, and we can say that ds equals 1 plus dy dx squared, which I'll write like that, times dx. Right, so this I just put under, combined them so that dy dx is squared. Dx squared, I'm using this rule here, I split this into two separate radicals, and then the square root of dx squared is dx, right? Dx squared under a radical is just dx. So this is what we get for ds. So ds is this. So the limiting value of that arc length delta s is ds. And what we're going to do with this, we're going to sum all of the ds pieces using integration to find the length of the curve. Okay, so there's a couple ways to come up with this formula. I just think this is the more intuitive approach. There's definitely a more rigorous approach that many books take, but I think this intuitively makes sense, and it's pretty good. We get to the same place, but we'll have a kind of a good intuitive understanding of what's happening. So this is the formula that we're going to use in this section. So then if we look on the next page, we want to find the entire length of the curve. So we're going to take the sum of all the ds pieces from a to b, and this can be found by evaluating this integral from a to b, and the integral that we just found, dy dx squared dx. And just to note, this is just a derivative. We're going to take the derivative and square it, right? Dy dx is a derivative. We're going to square the derivative, add 1, put it under the square root, and then integrate. And as you can imagine, these formulas for arc length can get messy pretty easily. Okay, so in the textbook, some of the homework problems are going to say, to set it up and use a calculator. Others will say to set it up and solve by hand. And when the kind of were solved by hand are carefully chosen by the author, because it's not easy to come up with these that you can solve by hand. So we'll take a look at some though, and you'll get a feel for how they work. But there are a couple formulas here. So it says if f prime of x, the derivative, because remember we're going to have to take that derivative and square it. Remember, f prime of x means the same as dy dx, right? So if this derivative is continuous on the closed interval ab, then the length of the curve y equals f of x, where x is between a and b, is right here, the formula that we just talked about. But okay, this is more of the standard form of y equals f of x, right? A function y in terms of x. But we could also have x in terms of y. So when that happens, we have this other version of it. It's basically the same formula. We just changed to, differentiate between these two forms. We have C and D here, but it's basically the same, right? This would just be this x equals g of y, and so it's a dy problem. Okay, but this is basically, these are the arc length formulas that we'll use, and then we can try them out and see how to make this work. Maybe you guys were hoping there'd be more formulas, but that's it. Just those two little ones. That's it for this section. Hope you're not too disappointed. Okay, let's see. Sometimes the software just tilts for some reason, and it looks like it's a little tilted here, so we'll just have to make it work. So example 1 says find the length of the arc from x equals 0 to x equals 2 on the curve y equals x squared. We're all familiar with that one. Use your calculator to evaluate the integral. Okay, so use your calculator to evaluate the integral. That's easy enough. So to set this up, we've got y equals x squared. If y equals x squared, that's in other words like saying f of x equals x squared, right? So y equals x squared, we need to find dy dx. Well, dy dx is just 2x. So we're going to have to square that. So let's see, so the length here, length from a to b is from 0 to 2, and we have 1 plus dy dx squared, 2x squared, dx, and that is basically it. Or I suppose if you wanted to, you could say, okay, so this is equal to 0 to 2, 1 plus 4x squared dx. Now, we could solve this one by hand if we wanted to, right? Because we know how to do trig substitution. So we could solve this one by hand. I know that when you solve this one by hand, you end up with a secant cubed. So, secant cubed you have to do a little bit of work for, but we could definitely do it. But for this one, they just want you to use the calculator. So remember, on the TI-83 or 84, if we want to solve this one, what we have to do is go to the math button, right? Then from the math button, you go to finite integral. It's usually number 9. And there's a couple ways to input that in the calculator. So if you have the older version of the software, from there, so you hit math, 9, and finite integral comes up. I'll do it. In case you have the old version, you have to actually type in the function. So you'd have to go, second, you'd have to get the square root key. So you have the square root, and then you have 1 plus 4x squared. Then you close that to close the square root. And then you have to go comma x to tell it that's the variable you're going to use, and then comma 0, and then comma 2. And then if you have the other version of the software, it uses what's called math print. It's really easy to figure out, so I don't even have to really explain it. But either way you go, you should get an answer of roughly 4.6468. Okay, so I mean, some of them are just pretty easy. We use the formula, right? The square root of 1 plus dy dx squared, and from a to b, so not really too much to it. Okay, now this one's going to be a little more work, because look what they don't say. It doesn't say use your calculator, which means you've got to do this one by hand. And as I mentioned before, there's only so many ways you can set this up so that it's going to work well with arc length. So these are going to be carefully chosen, as I said. So let's go ahead and try this one out and see what happens. Okay, so this one is x in terms of y. So we're going to have to find dx dy, right? We're going to have to square that. So try that one. Don't wait, don't just have me do it. Go ahead and try it out, see what you get, and then check back. But basically, we need to find dx dy. Okay, so press pause, try it out, and then check back. Okay, so hopefully you tried this one out. And you saw, okay, so dx dy, I'm going to have to go, really this is 1 minus y squared to the 1/2 power, right? So really what this is saying is 1 minus y squared to the 1/2 power. So when I take the derivative, I've got the power rule, so the 1/2 comes down. So we get 1/2, 1 minus y squared to the 1/2 minus 1, which is minus 1/2. And then the chain rule kicks in and says, well, this thing here is not plain old y, so I need to multiply by the derivative of this, which is going to be negative 2y. Okay, and then from here we can see that we can cancel the 1/2 with the 2, and we end up with, let's see, we've got y, got a negative, and in the bottom, I'm just going to put this in the bottom, 1 minus y squared. The negative 1/2, I'm going to make it to the positive 1/2 and just put it down here. Okay, so that is our derivative. And now we have to use our formula. So the formula says that the length is going to be the square root of 1 plus dx dy squared. Right, so this is dx dy, so we have to square it. Okay, so the length of this curve is going to go from negative 1/2 to 1/2, because that's what's given right here. Y is between negative 1/2 and 1/2. And then I've got to go 1 plus this squared. So if I square this, okay, if you square this, first the negative is going to go away, so I'm going to get y squared on top. And when I square a radical, the radical just goes away, so we get 1 minus y squared on the bottom. So we basically get y squared over 1 minus y squared. This whole thing is under the radical, so you have dy. Okay, so what we've got to do from here is we have to clean this up somehow so that we can actually integrate this function. All right, so in one like this, to clean it up, I think we're going to have to get a common denominator, right? So we need to have a denominator of 1 minus y squared. So what I'm going to do is I'm just going to rewrite this 1 in the form of 1 minus y squared over 1 minus y squared. So we would have something like this, minus 1/2 to 1/2. And we'll have 1 minus y squared over 1 minus y squared plus y squared over 1 minus y squared. Okay, so it's the same thing, right? Instead of 1, we have this. But now we have a common denominator, so now I can add these. So 1 minus y squared plus y squared is just going to be 1. So we're going to get negative 1/2 to 1/2. And then we'll have 1 minus y squared. And the top, we're just going to have 1. Okay, so this is what we've got. And then there's something here. It's one of these integrals we don't see all that much. So I'm going to rewrite it a little bit differently. So you can see that I'm going to use that rule that we've seen in algebra class. So we know that if we have a over b under a radical, we can write it like this, right? So I'm going to do that here, but you think when I do it here, the square root of 1 is just 1, right? So when I do that same thing here, here's what we're going to get. We're going to get negative 1/2 to 1/2. We're going to have 1 on top, 1 minus y squared down here. This integral you've seen before. We don't see it that much, but it is when you learn in Calc 1 typically, although we don't see it much. But if you think about it, you may remember something called the arc sign or the inverse sign. So we can finish this one because this is really just the inverse sign of y. We can integrate that from negative 1/2 to positive 1/2. So that will give us the inverse sign of 1/2 minus the inverse sign of minus 1/2. Okay, so what this is saying is, just a little trig review. We want to know the angle whose sine is 1/2. The angle whose sine is 1/2. Okay, so here sine is positive, right? So we could say, okay, the angle whose sine is 1/2. Well, sine is positive wherever y is positive. So sine is positive up here. And the inverse sine function is defined here and here. So sine is positive here. Inverse sine is defined here. So we're going to be in this first quadrant. So I'm just going to draw an angle here and make the sine equal to 1/2. So that would be opposite over hypotenuse. And if you use Pythagorean theorem, you see that this is the square root of 3. Okay, this is a special triangle. So this angle right here, this is the shortest side, right? This side is longer, which means this is going to have to be the 30 degree and the 60 degree angle. So 30 degree, of course, is pi over 6. So we're going to get, this is equal to pi over 6 minus, now remember this is inverse sine of negative 1/2. It looks almost like a long fraction bar there, but that's a negative 1/2. So in this case, we're thinking, okay, sine is negative, well, y is negative down here. Inverse sine is defined here and here. So now we're in this quadrant here. All right, so maybe I'll just do this again. We are in this quadrant here. Sine is 1 over is 1/2, so it's opposite over adjacent, or sorry, opposite over hypotenuse. So this is going to be the square root of 3 here. Once again, this is going to be a 30-degree angle, pi over 6. But in this case, since it's coming from standard position, it's going to be negative, right? There'll be negative pi over 6. So this is going to be pi over 6 minus pi over 6, which is like a giant plus, which is 2 pi over 6 or pi over 3. Okay, so a little bit of trigonometry here. Remember, this angle going this way is going in the negative direction, right? So that's why this one here is going to be negative pi over 6. We can't go over here because remember, inverse sine is not defined over here. It's only defined here and here. So that's why we're using the negative pi over 6. Okay, so hopefully that one made sense. I think we'll try one more. So this is a problem that's in the Stewart book. This is problem number 14 in the 9th edition. This is problem number 12 in the 8th edition. It might have even been in the 7th edition. It's been around for a while. It's a pretty good problem. And it's one where you'll see the other sort of algebraic manipulation we're going to need. Because again, there's only so many ways these kinds of questions for arc length can be asked in a way that they can be done by hand. Okay, there's only so many ways you can do it because you're going to have to take a derivative, square it, add 1 to it, put under the radical, and have it still be something that we can evaluate by hand. Okay, so to get started on this one, I'm going to first just rewrite this a little bit. I'm going to write it as, I guess I'll go 1/8 y to the 4 plus 1/4 y to the negative 2. Because we're going to have to take the derivative, right? We're going to have to find dx dy and then square it. So I'm going to do that off to the side here. So let me just circle. Okay, here's the original problem. We're going to find the length of arc of this curve on this interval of y, where y goes from 1 to 2. All right, so let's see. I'm going to just kind of do some side work over here. So I'll say, all right, dx dy. Okay, I'm going to take the derivative of this for the power rule, so the 4 comes down, so I get 4/8, or 1/2 y cubed. All right, so you get 1/2 y cubed. And then over here, the negative 2 comes down, so you get negative 2/4, which is negative 1/2. So you get minus 1/2 y to the negative 3. Okay, so now I have to square this, dx dy squared. And I'm just going to write these next to each other. I'll write this twice and then use the FOIL method. Okay, so we've got this. You can use the FOIL method here. First times first is going to give us 1/4 y to the 6. Outside times outside will give us 1/4. So you get plus 1/4 y to the 0, right? Because 3 plus negative 3 is 0. Then in here we're going to get, oh, actually that was not a plus, was it? That was a minus. Okay, it's a minus there. Okay, inside times inside gives us another minus 1/4 y to the 0. Then last times last gives us a plus, because negative 1/2 times negative 1/2 is positive 1/4 y to the negative 6. Okay, over here, y to the 0 is 1, right? And y to the 0 is 1, so this is basically minus 1/4, which is minus 1/2. So we end up with 1/4 y to the 6 minus 1/2 plus 1/4 y to the minus 6. Okay, so then what we've got to do to find the arc length, we are going to have to add that to 1, right? Because it's 1 plus dx dy squared. So I'm going to add 1 to that. So I'm going to go into this radical. I'll have 1 plus all of this stuff. Okay, so we have this under the radical dy. Then we can clean this up a little bit because we've got a 1 minus 1/2, so it gives us a 1/2. So that's going to be 1 to 2, 1/4 y to the 6 plus 1/2 plus 1/4 y to the negative 6 under the radical dy. How are we ever going to integrate this by hand? Well, what's going to happen with a lot of these, you'll start to recognize this format because, again, there's only so many ways these questions can be asked. When this happens, we've got something under the radical. Wouldn't it be nice if that were a perfect square under the radical? Because then we could get rid of the radical. That sure would be fantastic if that were the case. So what we could do is see, is it possible to factor this somehow? So let's see. It sure would be really cool if we could somehow factor that. Let's see. So if you think of like the FOIL method backward, what could I multiply by itself? First times first to get 1/4 y to the 6. I don't know. Let's try 1/2 y cubed times 1/2 y cubed. And then last times last is going to have to be 1/4 y to the negative 6. Well, what if we just tried 1/2 y to the negative 3 and 1/2 y to the negative 3? And now we know outside times outside and inside times inside has to be 1/2. I don't know if we could ever get this lucky. I'm just going to put a plus here and a plus here and see what happens. Because I need the pluses there so that this would really be this thing squared, right? Because this times itself. But let's first FOIL this and make sure that this works. Okay, so just check it out. First times first will be 1/4 y to the 6. Okay. Outside times outside is going to be 1/2 y to, or no, 1/4 y to the 0. Inside times inside is also 1/4 y to the 0. Well, 1/4 y to the 0 is 1/4 times 1. So really it's 1/4 plus another 1/4, which is 1/2. And then last times last will give us 1/2 y to the negative 6, which is what we've got. Okay, so that's good news because what that really means, what we've really got here is 1/2 y cubed plus 1/2 y to the negative 3 squared under a radical, which means we can get rid of the radical and the square, right? So really what we'll have, once we get rid of those, is we will have equals 1 to 2, 1/2 y cubed plus 1/2 y to the negative 3 dy, which suddenly is a much easier problem. Right, this is just much easier. Once we get done with the algebra, we just have the power rule a couple of times. So I can integrate this. This goes up to 4, then I divide by 4, which is like multiplying by 1/4. So I would get 1/8 y to the 4. This one's going to go up by 1 to negative 2, then I divide by negative 2, which is like multiplying by negative 1/2, which gives us negative 1/4 y to the negative 2. And then this is just evaluated from 1 to 2. So we can plug those values in. And let's see what we get. We're going to get 1/8, 2 to the 4th, minus 1/4, 2 to the negative 2, minus, when you plug a 1 in, we just get 1/8 minus 1/4. Okay, so this is equal to 1/8 times 16 minus 1/4. Okay, so 2 to the negative 2. 2 to the negative 2 is 1 over 2 to the positive 2, which is 1 over 4. So this is times 1/4. And I'm just going to distribute the negative through, get minus 1/8 plus 1/4. So we get a lot of arithmetic here. Of course, you can use your calculator at this part, right? But 16 over 8 is 2, minus 1/16 minus 1/8 plus 1/4. So I'm just going to get these all to have common denominators of 16. So I'm going to go 32 over 16 minus 1 over 16 minus 2 over 16 plus 4 over 16. And that would give us, let's see, 32 plus 4 is 36. Minus those three would be 33 over 16 for our answer. So, all right, this sort of process that happens here where you get a perfect square will happen. So that'll be fairly common. But 8.1 is just a couple formulas to use. So we developed them. So you should kind of know where they come from, and some algebra and some integration. So go ahead and give 8.1 a try. And if you run into any trouble, just let me know, and I will talk to everyone soon.